All right, so this is section P3 again, but we're doing the last portion of it. And this is odd and even functions. So these kinds of functions that we're going to be talking about are really, really important because if you do take more math in the future, you'll probably very likely learn that any function can be written as sums of these kinds of functions. So in a way, if you understand these functions, it'll help you a lot in understanding just regular general functions. Not only that, these two kinds of functions are very simple in that they each have a very nice property that tells you a great deal about its symmetries. Okay, so let's just start. The idea here is let's start with even actually. So even functions. So an even function is a function that just in terms of the picture, we'll talk about the algebraic aspect in a few minutes. So that's actually going to be the one that's really important. Even functions are ones that you have x, y. If you look at its graph, maybe something like this and like this, the part that's to the right of the y-axis, so this portion to the right here is a mirror image of the portion of the graph to the left of the y-axis. All right, so there's this kind of mirror symmetry about the y-axis. All right, so this is an example right here that I've drawn of a function that is an even function. So this guy is even. All right. We'll go a little more in depth into this, but let me draw a couple more examples. So x and y. So maybe something like that, and then or something like that, something like that. That's another even function. Everything on the right side of the y-axis is a mirror image of everything on the left side. All right. So kind of to be more specific, if you look at, for example, that point right there, right, you look at the corresponding point on the other side of the y-axis, it's exactly at the same position, except of course at a negative x location. All right, most functions are not going to be even functions. If I just close my eyes, I guess I should label this. If I close my eyes and just draw a function, then the graph of a function, then it's not going to be even. So something like that, that's not even because, well, there's no symmetry on the left side and between the right side and left side of the y-axis. All right, so these two sides in this case are not mirror images of each other. And by the way, another way to say the mirror image is that if I take, for an even function, if I take, for example, the left-hand side right there, and I flip it kind of like a page in a book, if I flip it to the other side, the graph should lie exactly on top of the other side of the function. All right, so that's just another description of how to visualize even functions. So this guy here is not even. So again, most functions are not even. So even functions are actually very special. You really, really like to work with even functions because, well, you can kind of see, in a way, if you want to study this function, your life is a lot simpler because you only have to study, in a way, half of it, right? If I understand the right side of this picture, then automatically I understand the left side of the picture, right? Whereas for this function down here, which is not even, understanding the right side of the picture tells me nothing about the left side of the picture. Okay. All right. So we are going to talk about the algebraic aspect of this because we definitely, so this is all picture based so far, but what we ultimately want to be able to do is if I give you a formula for a function, you should be able to tell whether that function is even or odd without having a picture available to you. Because I guess I've said this before, generally, we don't have pictures for functions. It's very hard to get a picture for a function. It's a big chunk of if you are going to take calculus, it's a major application in calculus, the first calculus class that you would take. So certainly for us, we have no idea what a function looks like. So we have to work with formulas. All right, but the picture is really good for motivation and kind of understanding the basic idea behind the concept of an even function or an odd function, which is what we're going to talk about next. So an odd function also has a kind of symmetry. So again, we're going to go by just the picture first. An odd function would look something like that. All right. So here again, for both even and odd functions, we're comparing what's happening in terms of the picture on the right side of the y-axis with what the graph looks like on the left side of the picture. All right. But for this guy here, we don't have this direct symmetry that we had in terms of the even functions, right? The right side here is not exactly a mirror image of the left side. In fact, if I were to create if I wanted to create a even function, right, given just this right-hand side, it would the other side would have to look like that, right, in order to keep the symmetry. All right, so this guy is definitely not an even function. All right, but what's the thing that makes it odd? Again, we look at a point to the right of the y-axis, and we look at the corresponding point on the other side. All right. For an even function, the value of the function would be exactly the same on the other side. But for an odd function, the value is exactly the same except negative. All right. So let me put in some numbers just so we can get an idea. If this point is 3 and that point is -3, those are the 2 points that we want to compare, or the 2 inputs that we want to compare. If this height here, let's say, is 10, then this height here would have to be -10. All right. So whatever value you get on one side, then on the opposite side, you should have negative of that value. All right. So another kind of sample point here, perhaps if this point here is 2, and that height right there is, let's say, 8, then at -2 on the other side, the value here would have to be -8. All right. So it's a little more complex than the concept of a even function, but it's just as important. All right. So you have this kind of symmetry, but flipped, right? So one way you can actually think about an odd function is you can take, if I take this right side here, and I flip it to the other side, to the left side, as a mirror, then it would have to look like that, right? And if the function did look like this on the other side, like I said, it would be even. But now if I flip it again, except up and down, right? So the first flip was across the y-axis. The second flip is across the x-axis, all right? So if I flip the second flip, I would end up down here. And if after 2 flips, I'm actually matching what's happening on the left-hand side, then it's an odd function. All right, so for example, let's start with just one side of the function first. Let's say, let's do something simple actually. Let me do this guy right there, or let me make it a little more exaggerated. There. All right, so let's say my function, its graph on the right-hand side of the y-axis is just this straight line here. What would the other side have to look like for the full graph to be an odd function? Well, it would have to look like this. So first, I flip it across the y-axis. I would get this guy right there. And again, if the left-hand side of the function looked exactly like this v, then it would be an even function. All right. But we're not looking for an even function. We're looking for an odd function. So I flip again with respect to the x-axis this time. Let me label these x and y. So if I flip it with respect to the x-axis, it would look like that. All right. So if I put these two together, then this would be an odd function. All right. So in other words, if the graph of my function indeed, the full graph of my function indeed was a straight line that went from here all the way up to there, then I would have an odd function. Okay, and again, if you plug in points, let's say I plug in 1 here and I get the output 4 there, then if I plug in -1 there, then the output here would have to be -4. All right. And in the same way, I've always been doing it kind of comparing, starting with the right-hand side, but you don't have to. If I start with the left-hand side here, if this were -2 and this height here were, let's say, -7, then that means the right-hand side would have to be the same pattern, 2, and up here would have to be 7. All right. Okay. So that's the idea behind an odd function. So let me label this odd function. But again, just like with even functions, it's really special to be an odd function. Most functions are not odd, and it's really easy if I just close my eyes and I draw a function, a graph of a function, let's say like that, it's not odd. All right. This one actually is pretty close to being odd, but it's not. For example, if I look at this point right there, let's say -1, it looks like I have to go very far up to hit the graph, right? Whereas on the other side, the corresponding point 1, I only go a little bit to hit the graph, all right? So the value at -1 is not the same as the value not the negative of the value at 1, and so it's definitely not odd, all right? In terms of our kind of pictorial flipping idea, let's say I flip the right-hand side across the y-axis, then I would get something that looks like that, right? And then if I flip it across the x-axis, I would end up with something that looks like that, right? So if the graph had looked like this from the beginning, let me shade it in a different color. If the graph had looked like this red thing in the beginning, then it would be actually an odd function, all right? But it's not. Okay, so that's the picture idea behind the even and odd functions. Like I said, most of the time we don't have pictures. We only have to have formulas to work with. And so the question is, in terms of kind of the algebraic description of a function, how do we tell whether a function is even or odd? All right, so let's start with even again. So here's the algebraic description. A function, f of x, is even if, so here was the idea. You were even if whenever I plugged in a point on this side, let me call it x, all right? Then on the opposite side, I would have, kind of the corresponding point on the opposite side, I would have the point -x, right? So if x were 3, then on the right-hand side, then on the left-hand side, that would have to be -3, okay? So you're even if you have the symmetry, right? So like we said, that means that whatever value I have at x, I have to have the exact same value at y. At -x. Okay. So this guy here, that point right there has height f of x, right? That's the definition of kind of the graph, right? You're on the graph if your coordinates are x comma f of x. And so if f of x is equal to that value right there, then f of -x has to be the same exact value, okay? And so our algebraic description is that f of x compared to f of -x, right, they have to be the same value. So these two guys have to be equal, okay? So this is a little abstract, but just as an example, that would mean, so this is for every, I guess I should really emphasize, this is for every x, all right? So it's not good enough to just have this equality, at one location or two location, or x equals 10 or x equals 7. It has to work for x equals 10 and x equals 7 and x equals 5 and x equals 1, every single x, all right? So in particular, if I know a function is even, then I know immediately that f of 3 is equal to f of -3. All right, let me write this here. If f is even, then this is the case, right? And f of 5 is equal to f of -5, and f of 1/2 is equal to f of minus 1/2, and so on. Okay, so the values, whatever you plug in, right, f of minus of that has to be the same output. Okay, and again, this makes perfect sense when you consider our definition of even, right? If this guy right here is an even function, it has the symmetry, right? So the value here is the same height as the value there. Otherwise, we wouldn't have the symmetry that we're asking for. Okay, so it's now clear how we can determine whether a function is even or not algebraically, in that we just check, is this statement here true or not, right? If I give you a function with a formula, f of x equals whatever, sine x, cosine x, x plus sine x, whatever it is, and we'll be seeing a lot of these examples in this section and in the corresponding Math 120 section this week. How would you check whether it's even or not? You check whether this statement here is true or not. If this statement is true for every single x, then it's even. All right. If there's even one input where it's not true, then it's not even. Okay, because you have to have the symmetry everywhere. All right. Before we do any examples there, let's look at in contrast the algebraic description of what it means to be odd. And then we'll do a bunch of examples for actually checking it. A function f of x is odd if what? Well, again, the idea behind even and odd, a really good way to think of this is it's always a comparison between f of x and f of minus x. All right. So for even, the comparison was that f of x was literally equal to f of minus x. Okay. What about odd? So again, this will be for every x. All right, and I'll fill in the middle part in just a couple seconds. But before we do that, let's look at the picture. So an odd function, here's an odd function right there, right? We've got this kind of symmetry in two ways, in a way, right? You flip across the y and you flip across the x. What does it mean? What's the kind of description of what's going on? Well, if we plug in 3 here, and that output is, let's say, 2, we said that on the other side, when we plug in minus 3, this output has to be minus 2. Okay, so here we're looking at the input 3 versus the input minus 3. Okay, so that would be like looking at, in terms of algebraically, that would be like looking at x versus looking at minus x. All right, now the outputs for the first one, f of 3 here, is 2, right? And so what we're saying is, it's 2. And on the other side, it has to be minus 2, right? Let me make that a little bit more obvious here. So this is minus 2 here, right? So the output on the other side, f of minus 3, has to be minus 2. Okay, what's the relationship between 2 and minus 2? They're negatives of each other. And so what we're looking for in general is f of x, the relationship between f of x and f of minus x is that they're negatives of each other. So for example, that, all right? Or you can write it the other way, like that. It's the same thing, okay? Of course, because if you multiply minus 1 on both sides, oops, sorry, I put that in the wrong place. Minus there, all right? It's the same thing because you multiply minus 1 on both sides, you get the same thing. All right. So again, algebraically, we now have a method for determining whether a function is odd or not, right? And again, this formula here will work. Checking this formula will work whether we have a picture or not. All right, so it's super powerful. Okay, so let me just summarize in words whether, a function is odd or even depends on the relationship between f of x and f of negative x, all right? Again, between the input on this side, right, maybe positive 3, and the input on the other side, which is negative 3. Or the input on this side, 1/2, versus the input on the other side, minus 1/2, right? Or the input on this side, 10, versus the input on this other side, minus 10, okay? And if the relationship is that they're equal always for every single input x, then it's even. If the relationship is that they're negatives of each other always, then it's odd. All right, so I think this is a very good way to, this statement here is a good way to remember what odd and even are about, what the concepts are about. Okay, so let's try to figure out, for some algebraic examples, whether a function is even or odd, or neither, right? Like I said, most functions are neither. Okay, so let's start with this example. Is f of x equals, let's say, x to the fourth, odd, even, neither? Okay, so that's our question. Oh, by the way, with one exception, odd, once you know a function is odd, it cannot be even, right? And same way goes in the other direction. If you know a function is even, then it cannot be odd, all right? And there is one exception. You should think about it yourself. What is the one function that can be both odd and even, all right? Okay, so what that means in practice is normally if you want to answer this question, you don't actually have to check necessarily all the possibilities, right? If I somehow determine that this guy is odd, then for sure it's not even, unless it's that one special function. And of course it's not neither, all right? Or if this function happens to be even, then I don't have to check that whether it's odd or not, all right? Because it's definitely not going to be odd, except for that one special function, which again, you should sit down and try to think about it yourself. All right. That special function is super, super simple. So it's not going to be, certainly not going to be any of the functions that we're going to be looking at today with kind of complicated formulas. Okay, so let's check. I'm going to actually check both just so we can see how it's done. But again, once you've determined one of them, you don't have to check the other if it is odd or if it is even. All right, let's check. Let's check even first. All right. So what does it mean to be even? What we have to check is, so we need to check f of x, is this equal to f of negative x? All right. So this is the notation I'm always going to be using for when I'm asking a question about whether two things are equal. I'm going to put a question mark on top of the equal sign. All right. You should definitely use the same kind of notation because if you put an equal sign, then it's really easy to kind of confuse yourself later on in the problem, because when you put equal signs, you naturally think the two things are equal. But we're actually trying to determine whether they're equal or not, right? So that's why I highly emphasize this question mark. We don't know whether it's equal or not. We're trying to check, okay? All right, so is f of x equal to f of negative x, right? So that's how I would read this here. Okay, so this is equivalent to asking, well, I'm just going to plug in the formula for f of x, right? F of x is x to the fourth. So this is the same as asking, is x to the fourth equal to f of negative x is what I get. Well, what is f of negative x? F of x is the function that whatever you put in, you take it to the fourth power. All right. So I'm putting in minus x. So I have to take minus x to the fourth power. All right. Okay. So our kind of odd even, or our even question boils down to, is x to the fourth equal to negative x to the fourth? like that. Okay, this guy here, the right-hand side, we can see it simplifies very well. This is x to the fourth. Is this equal to, well, minus 1. I'm going to write it in a few steps just to emphasize what's going on. This is minus 1 times x to the fourth, right? That's what minus x means. And this is x to the fourth. Is it equal to minus 1 to the fourth times x to the fourth? All right, that's how powers work. And so this is the same as x to the fourth. Is this equal to, well, minus 1 to the fourth is 1, right? Because minus 1 squared is 1. Minus 1 cubed is going to be minus 1. And then minus 1 to the fourth is going to be 1. So this is the same as asking, is x to the fourth equal to x to the fourth? All right. So the reason why we wrote it out like this was this answer here is yes, right? The answer to this question mark here is yes. These two are equal. And so the answer to the one above is yes. And so the answer to the question above is yes. And then above that, the answer is yes. And above that, the answer is yes. Okay. And this is for every single x, right? It doesn't matter what x you plug in. X to the fourth is going to be the same as x to the fourth. And so we've confirmed that no matter what x you plug in, f of x is equal to f of negative x. And so this guy is even. So f of x equals x to the fourth is even. Okay, because the answer to this final question was yes. All right, how would we do this question? So at this point, we can, if this was a homework problem, you would just stop, right? Because you know it's not going to be odd. So if we were to try to check whether it's odd, this is how we would do it though. All right, just so we can see a situation where it doesn't work. So what does it mean to be odd? It's the comparison between f of x and f of minus x, right? And what they have to be, the relationship between them has to be that they're negatives of each other. All right. And again, it doesn't matter which side I put the negative sign on. Let me put it on the right side in this case. Okay. Because I put it on the left side earlier, and I just want to emphasize it doesn't matter which side. Okay. All right. So again, we're checking whether this is true or not. So I put a question mark up here. All right. And again, my function, I'm still working with the same function. So f of x is x to the fourth. And now I'm asking, is this equal to negative of minus x to the fourth? Like that, right? Negative of f of x. Sorry, negative of f of negative x. All right. Okay. Let's simplify this. So this is the same as that, which is the same as x to the fourth. Is this equal to negative of, and I'm just going to do literally the same thing, minus 1 to the fourth, x to the fourth, right? But minus 1 to the fourth is 1. So this is asking, are these two guys the same? Minus x to the fourth. All right. For every x, right? So again, this is always for every x, every possible input. And here we can see that this is not going to be true, right? Because if I plug in x equals 1, then on the left side, I'm going to get 1. But on the right side, I'm going to get minus 1. Okay. So this means that there's a 1 point, right? X equals 1, where this this question mark here, the answer is no, right? And as long as there's 1 point, the whole thing is no, right? In fact, though, this particular function, almost every point will also fail, right? X equals 2, the left-hand side is 16, the right-hand side is negative 16, not equal again, right? So when you suspect something is not even or odd, what you do is you find a point where it fails. And then once you found a point where it fails, then that means the whole thing fails, right? So here, what I can say is x equals 1. Let me write it like this. For x equals 1, these are not equal. Right? So not odd. Okay. Because again, if you fail at one point, then you completely fail altogether. All right. Okay. A couple things to emphasize. So notice here in this last question mark that if I plug in x equals 0, they will be equal, right? 0 to the fourth is the same as negative 0 to the fourth. But that's not enough to confirm whether it's even or odd, or odd, because to be odd, it has to work for every input. So just because you find one input where it works, that tells you nothing at all. All right. To be odd, you have to work for every input. Okay. However, if you find one input where it doesn't work, then the whole thing fails. All right. So there's this kind of difference between determining whether something is odd and determining whether something is not odd. All right. One of them, in a way, is harder than the other, because one of them you have to check every x. The other, you can just find one x where it doesn't work. Another comment here is that I chose to kind of plug in x equals 1 at this final step right there, because I kind of could recognize that it's not going to be odd at that point, right? It's not going to be odd. And so once I feel like it's not going to be odd, then I plug in a point to kind of confirm that. But if you're not sure, just keep computing, right? Keep computing until you get to the point where they're obviously equal, or to the point where they're obviously not equal, right? So here, if I, for whatever reason, if I didn't recognize that these two are not equal, then I could just continue. My next step perhaps would be to throw the x to the fourths all to the left side, right? And so this would be the same as asking, is 2x to the fourth equal to 0, right? And now it's maybe even more obvious, because we're saying here in this last statement, is 2x to the fourth always equal to 0, no matter what x is, right? And it's pretty obvious that actually the only x where this is true is x equals 0, and no other x will work. Okay, so keep on going. If you're not sure whether you can make a conclusion yet, keep on simplifying until you can make a conclusion. Okay. All right. So let's do a few more examples. So let's look at f of x equals, let's say, 3x minus 2. All right. So let's ask, is this odd? Is this even? Is it neither? All right. So let's check even first. Right. So the question is f of x equal to f of negative x always for every single x? Right. Well, that's the same as asking, is 3x minus 2 equal to 3 times negative x minus 2, right? For every input x. Okay. If it's not clear at this moment, let's just do some cleanup. This is the same as 3x minus 2. Is this equal to minus 3x minus 2? If it's not clear, keep on going. 3x, is this equal to minus 3x? We cancel the 2's on each side, right? Because this 2 is the same as that 2 right there. We see 2 3's, right? We can cancel those if we're not sure at this moment. The question is x equal to negative x? Right? And if we're still not sure, we throw the x to the left-hand side. Is 2x equal to 0? Right? And if we're still not sure, we can keep going. Is x equal to 0? Right? And again, this is asking, is x equal to 0 for every x? Right? So all of these, technically, you should be writing for every x, for every x, for every x on every line. But we're just a little lazy, so I'm just going to emphasize it in this last line. All right? And here, now at this point, it's really obvious that it's false, right? Because, let me write this. No, right? Because x equals 1 fails. Let me just write it like that, right? When x is 1, 1 is not equal to 0. Okay? And so the previous one is no as well. No as well. No, 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 and no. And so this guy is not even. Okay, so this process is very typical of math, right? We have a kind of a hard question at the top, this one right here, that's very abstract and it's not easy to answer. So we make it into an easier problem and then an easier problem and an easier, easier until we get to the point where it's obvious what the answer is. And because each of these problems were equivalent to each other, answering any one of them, answering this last one, will answer all the ones above with the same answer. No, 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 no. Okay. All right. Let's see if this is odd then, right? If it's not even, maybe it's odd. So the question would be, is f of x equal to negative f of negative x, right? So is the relationship between the two outputs the negatives of each other? That's a way to remember it. So this is the same as asking, is 3x minus 2 equal to negative of 3 times minus x minus 2? Okay. And this is the same as asking, is 3x minus 2 equal to negative of minus 3x minus 2? That's the same as asking, is 3x minus 2 equal to 3x plus 2, right? And that's the same as asking, well, we have 3x, we can subtract 3x on both sides. The 3x's disappear. So this is the same as asking, is minus 2 equal to 2? Well, obviously the answer to this is no, right? 2 is definitely not equal to minus 2. And so the answer above is no. The answer above is no. The answer above is no. And so the answer above is no. Okay, so this guy is not odd. In fact, what this 2 equals minus 2 is saying is that this statement up here, f of x is equal to minus f of negative x, is actually never true. So any x will fail. All right, so I can pick any x. So x equals 12, right? Just a random number. So x equals 12. What do we have? F of x is equal to 3 times 12 minus 2, which is 36 minus 2, which is 34, right? Let me explicitly write f of 12. F of negative 12 is 3 times minus 12 minus 2 equals minus 36 minus 2 equals minus 38, right? These two guys, 34 and minus 38, are not negatives of each other. And so this is an explicit example of a value where you don't have the correct type of symmetry. All right. Okay, so this guy is not odd either. Oops, not odd. All right, so for this particular problem, this guy is neither. So f of x equals 3x plus, was it minus or plus? Minus 2. All right, sorry about that. Minus 2 is neither odd nor even. Well, I guess I checked even first, so let me write it in this order. All right. So again, this is the typical case. Most functions are neither even nor odd. By the way, we know this is true in terms of the picture, because what is f of x equals 3x minus 2? Let's think about kind of the graphing that we did. F of x equals x looks like this, right? Let me call this f0 of x equals x. All right, it's just a line at 45 degrees with the x-axis. So if I do this, if I replace x with 3x, then I'm going to end up, so what does this do? So these words, well, first of all, end up with a function where I have f1 of x is equal to f0 of 3x is equal to 3x, all right? And what that does is it compresses my above function by a factor of 3 towards the y-axis, right? So what happens is, let me do the previous function here. And what's going on is it's being compressed towards the y-axis by a factor of 3. And so I end up with this graph right here. Okay, So this is 3x. And then if I graph the next step, add minus 2 to output, all right, I would end up with the final function f2 of x is equal to f1 of x minus 2, which is, what's f1 of x? It was 3x minus 2, right? So this is the function that we want to graph. Okay, what does that look like? Well, I would take the previous steps function, and let me draw that with a red dotted line here, and I would shift it down 2 steps, down 2 steps, down 2 steps, down 2 steps, down 2 steps. And so my graph would actually look like that. All right, so this is the graph of 3x, f of x equals 3x minus 2. And the point here is you can see in terms of the picture, it's not even because, for example, if I plug in this value, my output is positive, whereas for it to be even, the output on the other side would have to be the same positive number. It's not, it's actually a negative number. Okay, so it's not even, and it's not odd either, because if I plug in this number again, the output should be at the same position, right, but negative. But it's not, it's much further down. All right, so this guy is, from the picture, it's neither even nor odd. Okay. All right, so for some of these problems, you can kind of confirm your answer, your kind of algebraic computations by graphing. Okay, and that's a nice exercise in graphing. All right, let's do a couple more. So what about is f of x equals, let's say, 2x cubed plus 5x, even or odd, or neither. All right. Okay. So let's check odd. All right. So odd. So that would be f of x. The relationship for odd is f of x and f of negative x should be negatives of each other. So I should put a minus sign there. And we're checking. So let's put a question mark there. This is equivalent to asking, is 2x cubed plus 5x, is that equal to minus 2 of minus x cubed plus 5 of negative x, right? Why? Because f of x is a function that whatever you give me, I cube it, and I multiply 2, and then I multiply 5 to it, and then I add the 2 results, right? So in this situation, you're giving me negative of x, so I have to cube negative of x, multiply 2 to it, and then add 5 times negative x. All right, so this is why you want to be very, very careful when you're working with functions, and you definitely want to understand the difference between f of x and f of negative x. All right. Okay, in any case, this is the same as 2x cubed plus 5x. Is this equal to minus? And then, well, minus x cubed, we got, if you think of it just as a cube as multiplying it by itself 3 times, that means you've got 3 minus signs. So altogether, that's 1 minus sign, right? Because minus 1 times minus 1 is 1. And if you times another minus 1, you get minus. So this is going to be minus 2x cubed. And then 5 times minus x is minus 5x. All right. Okay, let's keep going. 2x cubed plus 5x. Is this equal to? Now I'm going to distribute the minus signs in. So I get 2x cubed plus 5x. Are these two equal? Yes, they're literally the same thing. Okay. In fact, if I wasn't sure, I could even just go one more step, subtract the 2x cubed on both sides, subtract the 5x on both sides, and I would be asking, is 0 equal to 0? And that's certainly yes, right? And so the next one is above is yes, this one is yes, this one is yes, this one is yes, and so this guy is odd. Okay. And so what that means is we don't have to check even at all, because we know that if you're odd, you can't be even, aside from the one example that you've discovered, hopefully. Okay, notice one thing here is that this example, it was not one that you could graph, right? We don't know how to graph this function here because there's a 5x right there. And so this is the only way you can do this problem. There's no chance of kind of figuring it out graphically. All right, let's do one more. So is f of x equals, let's say 1 plus 1 over x squared, even, odd, neither? Okay. All right. So again, let me check whether this is even. So that would be asking, is f of x, the relationship between f of x and f of negative x, are they equal? Okay. So this is the same as asking, is 1 plus 1 over x squared, is that equal to 1 plus 1 over minus x whole thing squared, right? Is that this, and that's the same as, is this guy equal to 1 plus 1 over negative x squared is the same as just x squared, the minus ones cancel. And here again, we can see that literally the left-hand side is the same as the right-hand side. And so the answer to this is yes. All right. And so that's yes. And so that's yes. And so this is even. So f of x is even. Okay. And again, once we discovered that it is even, we don't have to check whether it's odd. Okay. All right. So all of the problems in this section are of this type for this week, the homework problems. Definitely go through these very carefully and kind of reason these out, make sure you're okay with them. Okay. For the trig portion of this, for the trig math 120, we're going to be talking about sine and cosines, and they're going to be cosine is going to be even. We've actually already seen the graphs of cosine and the graphs of sine, which is odd, and then we'll also talk about tangent. But this is the core for that material, and in the math 120 version of this, we're not going to go through all the same stuff. We'll just mention it a little bit because this is already kind of the baseline foundation. All right, so before I quit, here's something for you to think about. So let me write like this: knowing the graph of f of x equals x squared, right? We know the graph of this. You should know the graph of this, right? Is knowing, so this looks weird. Is it even or odd or neither? So that's the first question. Let me call this part A. So just from the picture, right? Without doing any algebra, just from the picture. Okay. All right. Now you can answer this. Is f of x equals x squared plus 1 even, odd, neither? And again, don't do any computations. Just think about the picture and think about graphing, right? What is the graph of this guy in relation to the graph of that guy? And you should be able to answer the question. All right. And then C would be, is f of x equals x plus 1 whole thing squared, even, odd, neither? All right. And again, try to think of this question graphically. What is the relationship between this graph and the graph of f of x equals x squared? And you should be able to answer the question. Okay. And after you've thought about these, it's a good idea to try to figure it out algebraically, as we've done above as well, just so that you're comfortable with kind of both aspects, the graphical and the algebraic aspects of odd and even.